The universe doesn't give up its secrets easily. Black holes that devour light, galaxies that shouldn't exist, signals from across the void we still can't explain. For centuries we thought we understood the cosmos, until discoveries started shattering every assumption. Each new finding reveals how little we actually know. What we're finding out there isn't just strange, it's rewriting the rules of reality itself. Over the next hour, we're exploring the cosmic mysteries that challenge everything we thought was possible. A black hole is one of the universe's most mysterious and fascinating objects. It's a region in space where gravity is so intense that nothing, not even light, can escape from it. This incredible pull is what makes black holes so intriguing. They are essentially invisible, revealing their presence only through their effects on nearby matter. Black holes form from the remnants of massive stars that have exhausted their nuclear fuel. When a star with at least 20 times the mass of our Sun reaches the end of its life, it undergoes a catastrophic collapse. Without the outward pressure generated by nuclear fusion, gravity takes over, causing the star's core to implode inward. This collapse compresses the core to an incredibly dense point called a singularity, where the laws of physics as we know them break down. Surrounding this singularity is the event horizon, the point of no return. Once anything crosses it, it's doomed to be pulled into the black hole. The process can also happen through other cosmic phenomena, such as galaxy collisions, where supermassive black holes grow by swallowing gas, dust, and even other black holes. Some black holes are millions or billions of times the mass of our Sun, lurking at the centers of galaxies, including our own Milky Way. The idea of an object with gravity so extreme that it warps space and time continues to fascinate scientists and space enthusiasts alike. Their existence challenges our understanding of physics and the fabric of reality itself. Despite their terrifying reputation, black holes are natural products of the universe's life cycle, continuously reshaping our understanding of what lies beyond the stars. Black holes are among the most mysterious and powerful objects in the universe, and their influence on surrounding space and matter is nothing short of extraordinary. When matter, such as gas, dust, or even entire stars, ventures too close, it doesn't just pass by unnoticed. Instead, black holes exert an immense gravitational pull, pulling in this material at astonishing speeds. As matter spirals toward the black hole, it forms an accretion disk, a swirling luminous band of heated gas and dust that radiates intense X-rays and gamma rays, making black holes some of the brightest objects in the universe when actively feeding. But the effects of black holes go far beyond just consuming nearby matter. Their gravitational forces can warp space-time itself, creating phenomena like gravitational lensing, bending, and magnifying light from objects behind them. These distortions can help astronomers detect black holes even when they aren't actively devouring matter. Moreover, when particles or gases fall inward, some of the energy is released in powerful jets blasting outwards from the poles of the black hole at nearly the speed of light. These jets can stretch across millions of light-years, sculpting their host galaxies and influencing star formation by either triggering or hindering it through the injection of energy and material into the intergalactic medium. Black holes also play a role in galaxy evolution. Their energetic outputs can regulate the growth of galaxies by clearing out or heating the gas that would otherwise collapse to form stars. They are cosmic engines that shape their surroundings in profound ways, from creating energetic emissions detectable across the universe to influencing the structure of entire galaxies. This dynamic interplay makes black holes not just collapse points of gravity, but active players that mold the universe on grand scales. Scientists have amassed a wealth of compelling evidence pointing to the existence of black holes, even though no one has seen one directly. The most convincing comes from observing the effects they have on nearby matter and light. For instance, astronomers have detected stars orbiting invisible objects at incredible speeds. These stars behave as if they're being tugged by something incredibly dense and massive, something that's too small to be a star itself. By analyzing their orbits, scientists can calculate the mass of these objects, finding they often contain the equivalent of millions or even billions of suns packed into a space no larger than a city. Another line of evidence comes from accretion disks, the swirling, glowing rings of gas and dust spiraling into black holes. When matter gets pulled inward, it heats up intensely, emitting X-rays that telescopes can detect. The pattern of these X-ray emissions fits models of black hole accretion, confirming their presence. In some cases, astronomers have even observed jets of high-energy particles shooting out from what appear to be black holes, further supporting the idea that these objects are powerful gravitational wells. More recently, the detection of gravitational waves has revolutionized our understanding. These ripples in space-time occur when two black holes collide and merge, releasing an enormous burst of energy. LIGO and Virgo observatories have recorded multiple such events. The signals match precisely to predictions made by Einstein's theory of general relativity about what merging black holes should produce. Additionally, the Event Horizon Telescope's groundbreaking image of the shadow of what is believed to be a supermassive black hole in the galaxy M87 offered a visual hint, an ominous dark circle against the glowing backdrop of inhomogeneous emission from surrounding plasma. All these observations form a consistent picture. Black holes are real, transforming the universe into an even more mysterious and fascinating place. Once something crosses the event horizon of a black hole, it's generally considered lost forever. The gravitational pull is simply too strong for anything, even light, to escape. This boundary marks the point of no return, and for decades scientists believed that nothing could break free once past it. However, the story isn't so cut and dry. In 1974, physicist Stephen Hawking proposed a mind-boggling idea. Black holes might not be completely black. Instead, they could slowly lose energy and eventually evaporate over incredibly long timescales through a process now known as Hawking radiation. Hawking radiation arises from the strange rules of quantum mechanics that apply even in the seemingly empty space around a black hole. Quantum theory suggests that pairs of particles are constantly popping in and out of existence all around us. Near the event horizon, these pairs can be separated by the black hole's intense gravity. One particle might fall into the black hole while the other escapes, effectively reducing the black hole's mass and energy over time. It's as if the black hole is leaking tiny amounts of radiation, gradually evaporating like a slow-burning ember. This concept shatters the traditional view that nothing can escape a black hole. Instead, Hawking radiation reveals that black holes are not entirely black. They glow faintly, radiating energy away. Interestingly, this radiation is purely quantum mechanical. It has nothing to do with the traditional way we think of black holes as cosmic vacuums, sucking in everything around them. It's a bridge between quantum physics and gravity, two realms that don't often meet. Over unimaginably long periods, Hawking radiation could cause a black hole to shrink and eventually vanish, leaving behind what was once thought impossible, the idea that black holes aren't completely permanent. Instead, they are dynamic and, in some profound ways, alive, slowly breathing out their secrets into the universe. Black holes often evoke a sense of fear, but the truth is, the black holes close to us are incredibly distant and pose no direct threat to Earth. The nearest known black hole is hundreds of light years away, far beyond the reach of any danger. These cosmic monsters are essentially vacuum cleaners of the universe, pulling in matter from their surroundings, but the likelihood of one wandering into our solar system is astronomically low. Even if a black hole were to come near our solar system, it would need to be surprisingly small and dangerously close to cause significant harm, which is highly improbable. Most black holes are billions of times more massive than our Sun, but they remain peaceful in the vast emptiness of space, simply existing without posing an immediate threat. Their implications for the universe are profound and fascinating. Black holes challenge our understanding of physics, especially at the intersection of gravity and quantum mechanics. They are like cosmic laboratories, where the laws of nature are pushed to their limits. The concept of event horizons, points of no return, raises questions about how information is preserved or lost in the universe, hinting at deeper mysteries about the fundamental fabric of reality. Furthermore, black holes may play a vital role in galaxy formation. Supermassive black holes sit at the centers of most galaxies, including our own Milky Way. They influence star formation and galactic dynamics, acting as anchors that help shape the universe's large-scale structure. Scientists are also exploring the possibility that black holes might be gateways to other dimensions or parallel universes, sparking even more curiosity about their nature. So, while they aren't a danger to us directly, black holes are like cosmic keys, unlocking secrets that could rewrite our understanding of the universe itself. Dark matter is one of the universe's greatest mysteries, an invisible substance that doesn't emit, absorb, or reflect light. It's like the cosmic ghost that we know is lurking out there, shaping the universe, even though no one has ever seen it directly. The reason scientists believe dark matter exists comes from analyzing how galaxies move and behave. When astronomers measure how fast stars orbit the centers of galaxies, they find something puzzling. The outer stars are moving much faster than they should, if only visible matter, stars, gas, and dust were pulling on them. According to the laws of physics, these stars should be flung out into space, but instead, they stay bound tightly, orbiting as if there's some unseen mass holding everything together. This mismatch between what they observe and what they expect from visible matter pointed to the presence of dark matter. It acts like a cosmic glue, holding galaxies together and preventing them from ripping apart at their edges. The gravitational effects of dark matter also influence the way light bends around galaxy clusters, creating what's known as gravitational lensing. When light from distant objects passes near these cluster formations, it bends more than it should if only visible matter were the cause. This extra bending confirms there's more mass out there than meets the eye. Furthermore, on the largest scales, the distribution of galaxies and the cosmic microwave background, the faint glow left from the universe's infancy, align perfectly with models that include dark matter. Without it, our understanding of how the universe evolved and how structures formed simply doesn't hold up. All these clues, galaxy rotations, gravitational lensing, and cosmic background measurements, come together to create a compelling picture. Dark matter makes up about a quarter of the universe's total mass energy, silently shaping everything in ways we're still trying to fully understand. Imagine the universe as a vast, expanding balloon, with galaxies like tiny dots drifting farther apart as it inflates. For a long time, scientists believed gravity, the pull between all mass, was the main force slowing this expansion. But then, they saw something surprising that changed everything. Dark energy. Dark energy is an invisible force that makes up about 70% of the universe. Unlike matter or radiation, which attract, dark energy pushes things apart. It acts like an anti-gravity force, stretching space itself. Think of it as an engine inside the universe that accelerates the galaxies outward at an increasing rate. What makes dark energy so puzzling is how little we understand it. We can't see it directly. It doesn't emit or absorb light. Instead, scientists detect its presence by observing the universe's accelerating expansion. Using precise telescopes and distant supernovae, researchers found that expansion isn't slowing down, as expected, but speeding up. This indicated a mysterious force working against gravity's pull. Dark energy's influence is profound. It drives the universe to grow faster, preventing gravity from causing a collapse. Without dark energy, the universe might have slowed and eventually contracted. But with dark energy dominating, its future is uncertain. It could continue expanding forever, growing colder and more diffuse, fading into a silent, lonely place. Some theories even suggest more bizarre outcomes, like a universe tearing itself apart in a catastrophic event. Understanding dark energy remains one of modern cosmology's greatest challenges. Each discovery brings us closer to unraveling the universe's fabric, revealing a cosmic story far stranger and more beautiful than imagined. Its secret lies at the edge of our knowledge, hinting at mysteries we are only beginning to grasp. Dark energy shapes our universe's fate, and unlocking its secrets may redefine our understanding of reality itself. Imagine peering into the vastness of space and realizing that the matter we can see, stars, planets, galaxies, makes up only a tiny fraction of the universe's total content. That's right. The cosmic landscape is overwhelmingly dominated by invisible components known as dark matter and dark energy, and scientists have only begun to comprehend their mysterious nature. Dark matter accounts for roughly 25% of the universe's total mass energy. It doesn't emit, absorb, or reflect light, making it invisible to telescopes. Yet, its presence is felt through its gravitational pull. When astronomers observe how galaxies rotate, they notice that stars at their edges move faster than they should, if only visible matter were present. This discrepancy points to a vast halo of dark matter enveloping galaxies, acting like an unseen scaffold that holds everything together. Even more astonishing is dark energy, which makes up about 65% of the universe. If dark matter is the cosmic glue holding galaxies in place, dark energy is the mysterious force pushing everything apart. It's driving the accelerated expansion of the universe, a phenomenon first discovered in the late 20th century through observations of distant supernovae. This repulsive force seems to work counter to gravity, stretching the fabric of space itself at an alarming rate. Altogether, these invisible entities, dark matter and dark energy, constitute about 90% of the universe's total content. We exist in a universe primarily governed by the unseen, a cosmos where the ordinary matter we know is just the tip of the cosmic iceberg. Unlocking the secrets of dark matter and dark energy remains one of the greatest quests in astrophysics, promising to redefine our understanding of the universe's past, present, and future. Dark matter and dark energy are among the most elusive puzzles in modern astronomy, constantly challenging scientists. The main obstacle is their very nature. Dark matter does not emit, absorb, or reflect light, rendering it invisible to traditional telescopes. Researchers can only infer its presence through gravitational effects on visible matter, such as galaxy rotation speeds or light bending, known as gravitational lensing. These effects are subtle, requiring highly sensitive instruments and meticulous analysis to distinguish them from other cosmic phenomena. Deciphering how much dark matter exists and how it clusters is a monumental task, complicated further by the variation in its distribution across different regions. Dark energy presents its own challenges. It is believed to cause the accelerated expansion of the universe, yet its properties remain uncertain. Unlike dark matter, which can be studied indirectly through gravity, dark energy's effects are more uniform, making it difficult to pin down. Scientists observe distant supernovae, galaxy clusters, and the cosmic microwave background, but measurement uncertainties and model complexities hinder clear understanding. Its fundamental nature might involve unknown physics, such as quintessence fields or modifications to Einstein's general relativity, complicating the development of testable hypotheses. Because both dark components produce faint effects, experiments and telescopes must achieve extreme sensitivity and precision. These efforts require large collaborations, advanced technology, and patience, often spanning decades. Each new observation adds pieces to the puzzle, but the full picture remains elusive. The pursuit of understanding these dark elements is as much about technological innovation as scientific curiosity, an ongoing journey at the frontiers of cosmic knowledge. The challenges faced include detecting invisible matter through indirect signals, interpreting subtle gravitational effects, and constraining the properties of dark energy amid measurement uncertainties. Addressing these issues demands pushing technological limits and developing new theories, reflecting the immense complexity of uncovering the universe's hidden components. The mysterious realms of dark matter and dark energy are among the most captivating puzzles in modern astrophysics. Dark matter, which makes up about 26% of the universe, is thought to be some kind of invisible substance that doesn't emit, absorb, or reflect light, making it impossible to detect directly. One popular theory suggests that dark matter could be composed of weakly interacting massive particles, or WIMPs. These are hypothetical particles that rarely interact with normal matter, yet their gravitational pull influences the motion of galaxies, keeping stars from flying apart at the edges of those galaxies. Scientists are also considering the possibility of axions, tiny particles that could be a component of dark matter, or even more exotic options like primordial black holes, formed in the universe's earliest moments. Dark energy, on the other hand, accounts for approximately 70% of the universe and is a mysterious force driving the universe's accelerating expansion. The leading theory posits that dark energy is a property of space itself, often referred to as the cosmological constant, originally proposed by Einstein. This energy permeates the vacuum of space and exerts a repulsive force that pushes galaxies apart. Some scientists are exploring modifications to Einstein's general relativity, proposing that what we interpret as dark energy could actually be a result of new gravitational physics on cosmic scales. Still, others suggest that dark energy might be dynamic, changing over time, much like a field that evolves as the universe expands, which would imply a whole new realm of physical laws at play. While we're still far from fully understanding these enigmatic components of the cosmos, ongoing experiments and observations, from deep space surveys to particle detectors deep underground, continue to peel back the layers. Each breakthrough feels like a step closer to unveiling the true nature of the universe's most elusive constituents. Imagine an object so dense that a single teaspoon of its material would weigh billions of tons. Welcome to the world of neutron stars. These incredible remnants are born from the fiery death of massive stars. When a star even twice the size of our Sun runs out of fuel, it can no longer support its own weight. Its core collapses under gravity's relentless pull, squeezing protons and electrons together until they merge to form neutrons. This catastrophic implosion results in a neutron star, a celestial object with a mass about 1.4 times that of our Sun, packed into a sphere roughly 12 miles across. To put that into perspective, if you could place a neutron star in the New York City area, it would have a density so extreme that it would weigh more than all the people in New York combined. During the collapse, the outer layers of the star explode outward in a supernova, dispersing heavy elements into space. What's left behind is this ultra-compact core, our neutron star. Its mighty gravity is so powerful that it warps space-time around it, creating a landscape unlike anything else in the universe. Neutron stars often spin at dizzying speeds. Many rotate hundreds of times per second, thanks to the conservation of angular momentum during collapse. This rapid spin can produce intense magnetic fields, some 1 trillion times stronger than Earth's, turning these stars into cosmic lighthouses called pulsars. Neutron stars are laboratories of extreme physics, offering clues about the behavior of matter under conditions impossible to replicate on Earth. They serve as cosmic beacons, guiding scientists through the mysterious depths of the universe, revealing secrets about the fundamental fabric of the cosmos. From their fiery births to their rapid rotations and intense magnetic fields, neutron stars stand as a testament to the universe's capacity for mind-boggling extremes. Pulsars stand out as one of the most fascinating types of neutron stars, not just because of what they are, ultra-compact remnants of massive stars, but because of how they behave. Imagine a city's brightest lighthouse, sending out beams of radio waves at regular pinpoint intervals. That's essentially what a pulsar does. These stellar remnants rotate at astonishing speeds, sometimes hundreds of times per second, creating beams of electromagnetic radiation from their magnetic poles. As the star spins, these beams sweep across space like lighthouse beams, and if Earth happens to be in the path of these beams, we detect a rhythmic pulsing of radio signals, hence the name pulsar. What makes pulsars especially special is this precise timing. Their pulses are incredibly regular, more stable than the most accurate atomic clocks we have, and scientists can predict their signals years in advance. This incredible regularity allows pulsars to serve as cosmic clocks, helping us to test the laws of physics under extreme conditions, or even to detect gravitational waves passing through our galaxy. Another unique feature is their intense magnetic fields, trillions of times stronger than Earth's. These magnetic fields funnel charged particles to the magnetic poles, creating hotspots that emit beams of radiation. The rapid rotation combined with these magnetic poles gives pulsars their lighthouse effect. Some pulsars also show irregularities, glitches where they suddenly speed up or slow down, offering scientists clues about their internal structure, which remains a mystery in many ways. Pulsars can also be found in diverse environments. Some are solitary, floating through space alone, while others are part of a binary system, orbiting companion stars. These systems can produce even more exotic phenomena, such as the formation of millisecond pulsars, which spin at extraordinary rates, making pulsars not just unique, but endlessly intriguing objects in our universe. Scientists study neutron stars and pulsars by using a combination of advanced telescopes and innovative observational techniques across multiple wavelengths of the electromagnetic spectrum. Since these celestial objects emit primarily radio waves, X-rays, and sometimes gamma rays, astronomers rely heavily on radio telescopes to detect their signals. When a pulsar, a spinning neutron star emitting beams of radiation, sweeps its beam past Earth, it creates a remarkably regular pulsing signal, much like a cosmic lighthouse. These pulses can be incredibly precise, allowing scientists to measure their rotation periods down to millionths of a second. Such precision has even made pulsars useful as cosmic clocks, helping to test theories of gravity and detect gravitational waves. In addition to radio observations, Space-based observatories like the Chandra X-ray Observatory and the XMM Newton telescope allow scientists to peek into the high-energy environments surrounding neutron stars. These observations reveal hotspots on their surfaces, accretion disks from companion stars, and phenomena like magnetar bursts, intense X-ray flares from highly magnetic neutron stars. Scientists also study neutron stars and pulsars by monitoring their timing and spectral data over long periods. This helps them understand how these objects spin down over time, how their magnetic fields evolve, and how they interact with their surroundings. Sometimes, astronomers observe sudden changes or glitches in pulsar timing, which reveal information about the star's interior structure and the extreme physics under conditions impossible to replicate on Earth. Furthermore, gravitational wave detectors like LIGO and Virgo have begun to pick up signals from neutron star mergers, providing insights into their masses, compositions, and how they influence the fabric of space-time itself. Every photon detected, every ripple measured, brings scientists closer to unraveling the dense, enigmatic nature of neutron stars and pulsars, nano-sized laboratories that reveal the universe's most extreme physics. Neutron stars are among the universe's most fascinating and mysterious objects, and their interiors remain one of the biggest cosmic puzzles. Imagine a city-sized sphere packed with more mass than the Sun. That's what a typical neutron star is like. But what lies beneath its ultra-dense surface? That question keeps scientists awake at night. At the heart of the enigma is the state of matter under such extreme pressures and densities. The atoms have been squeezed so tightly that electrons and protons have merged into a sea of neutrons, creating a super-dense neutron-rich core. But is this the whole story? Could there be an even stranger layer beneath, perhaps a core where quarks, the fundamental building blocks of matter, are free to roam in a quark-gluon plasma? This state, theorized by physicists, might exist deep within the star, but it's incredibly difficult to confirm experimentally. Another mystery revolves around the star's crust, which is thought to be composed of a lattice of nuclei amid a sea of electrons. But what exactly is happening at the microscopic level? Are there exotic particles lurking in these layers? Could there be superfluid or superconducting regions inside? These superfluid layers might explain some of the star's mysterious behavior, like sudden speed-ups called glitches. But there's still so much we don't understand about how these layers form and interact. Even more perplexing is the question of whether neutron stars contain a phase transition, a sharp change in their internal state, possibly turning into even more exotic objects, like strange quark stars. If they do, it could completely change our picture of how matter behaves under the universe's most extreme conditions. Deep inside these stellar remnants, the rules of physics, as we know them, are pushed to their limits. Unlocking their secrets could not only reveal new realms of physics, but also shed light on the fundamental nature of matter itself. Imagine a celestial object so dense that a sugar cube-sized amount of its material would weigh as much as a mountain. That's a neutron star, an incredible remnant of a supernova explosion, packing more mass than our Sun into a sphere just about 12 miles across. Scientists wonder, could these cosmic powerhouses someday revolutionize space travel or technology? Neutron stars possess some astonishing properties. Their magnetic fields are trillions of times stronger than Earth's, creating phenomena that challenge our understanding of physics. Pulsars, a type of neutron star, emit beams of electromagnetic radiation with clock-like precision, acting almost like cosmic lighthouses sweeping across the universe. This extraordinary regularity helped scientists discover gravitational waves and map the universe's expansion. But what about their potential? Could we harness their unique features for our benefit? Some researchers envision using neutron stars' intense magnetic fields as giant magnetic sails, kind of like cosmic brakes, to propel spacecraft at speeds impossible with current technology. Imagine a spacecraft riding a neutron star's magnetic fields, gaining immense velocity without conventional fuel, cutting the journey to distant stars from thousands of years to mere decades. While these ideas are still rooted in theory, advances in understanding plasma physics and magnetic field manipulation bring them closer to reality. Beyond propulsion, the extreme environments of neutron stars could inspire breakthroughs in materials science. The matter within neutron stars, called neutron-degenerate matter, might hold secrets about creating ultra-strong materials, lightweight yet incredibly durable, useful on Earth and in future spacecraft. Moreover, Studying these stars helps us understand matter under conditions impossible to replicate otherwise, pushing the frontiers of physics and engineering. While harnessing neutron stars is still beyond our current reach, their very existence sparks imagination about what future technologies could achieve. Exploring their mysteries might someday lead us to unlock new ways of traveling across the cosmos, turning science fiction into science fact, and bringing the universe just a bit closer to home. Gamma-ray bursts are among the most energetic and mysterious phenomena witnessed in the universe. These intense flashes of gamma radiation can outshine entire galaxies for brief moments, releasing in just seconds what our sun would emit over billions of years. But what triggers such staggering explosions? The answer isn't straightforward, but scientists believe they often result from catastrophic cosmic events. One leading theory is that they occur when massive stars exhaust their fuel and collapse into black holes, unleashing jets of highly energetic particles that spew out at nearly the speed of light. Alternatively, when two neutron stars spiral inward and collide, the merger can also produce a short gamma-ray burst, accompanied by a burst of gamma radiation. Detecting these fleeting yet powerful bursts requires sensitive and specialized instruments. Space-based telescopes like NASA's Fermi Gamma-Ray Space Telescope and the Swift Observatory are key players. These observatories are equipped with detectors that can sense gamma rays, which do not penetrate Earth's atmosphere, making ground-based detection impossible. When a gamma-ray burst occurs, the detectors on these satellites instantly register the burst's intensity, duration, and energy spectrum. This data gets transmitted to Earth in real time, alerting astronomers worldwide. Once detected, astronomers scramble to point optical, radio, and X-ray telescopes toward the burst's location. This follow-up observation helps determine the burst's distance, origin, and the environment in which it happened. The precise localization of gamma-ray bursts not only helps uncover the catastrophic cosmic events behind them, but also provides invaluable clues about the early universe, star formation, and the conditions of distant galaxies. These fleeting cosmic explosions continue to challenge our understanding, reminding us that the universe holds secrets as explosive as they are enigmatic. Gamma-ray bursts are among the most energetic and mysterious phenomena in the universe, erupting with more energy in a few seconds than the sun will emit over its entire lifetime. So what causes these colossal explosions? The primary sources of gamma-ray bursts fall into two categories: the collapse of massive stars and the merging of compact objects like neutron stars. When a star much larger than our sun exhausts its nuclear fuel, its core collapses under gravity, triggering a supernova explosion. If the remnant core is dense enough, it collapses further into a black hole or a neutron star. This process releases an intense jet of high-energy particles and radiation that streams outward at nearly the speed of light. As these jets pierce through the star's outer layers and then travel through space, they produce the gamma-ray emission we detect as a gamma-ray burst. The other origin is the collision of two neutron stars, or a neutron star and a black hole. These cosmic mergers produce gravitational waves and unleash a powerful burst of gamma rays, often followed by afterglows in visible X-ray and radio wavelengths. The discovery of such mergers through gravitational wave detectors has confirmed that these cataclysmic events generate gamma-ray bursts. Why do gamma-ray bursts matter? They're not just spectacular fireworks. They serve as cosmic beacons illuminating the distant universe. Because gamma-ray bursts are so luminous, they can be observed across billions of light years, offering a glimpse into the universe's early history. They help astronomers understand the life cycles of the largest stars, the formation of black holes, and the behavior of matter under extreme conditions. Furthermore, gamma-ray bursts also challenge our understanding of physics, pushing the limits of models about how matter behaves at incredible densities and energies. Their fleeting but intense flashes illuminate some of the most extreme environments known, making them key to unraveling the universe's deepest secrets. Gamma-ray bursts are one of the most energetic events in the universe, releasing in just seconds what our sun emits over billions of years. When a burst occurs, it unleashes a powerful jet of gamma rays that races outward at the speed of light, piercing through the fabric of space with astonishing intensity. The immediate surroundings of a gamma-ray burst are transformed in a flash, as the intense radiation bombards nearby gas and dust, ionizing atoms and creating a wave of high-energy particles. This sudden influx of energy can drive shock waves through the interstellar medium, heating up gases and triggering complex chemical reactions that can influence the evolution of the surrounding environment for thousands of years. These bursts don't just leave a temporary mark, they can sculpt the very structure of their cosmic neighborhoods. The radiation pressure can push material away, carving out large cavities or bubbles in molecular clouds, regions dense with star-forming material. This can either halt star formation temporarily by dispersing the gas, or paradoxically, trigger new stars to form by compressing nearby clouds. The aftermath also leaves behind an afterglow, an expanding shell of energized particles that slowly fades over time, but can be observed across many wavelengths, from X-rays to radio waves. For planets and potentially life in their vicinity, gamma-ray bursts can be catastrophic. The intense radiation can strip away atmospheres and obliterate surface life if a burst occurs too close. But from a broader perspective, these cosmic explosions serve as both destructive forces and cosmic catalysts, shaping galaxy evolution and influencing star birth on grand scales. They remind us just how dynamic and interconnected our universe truly is, where even the most destructive events can pave the way for new beginnings. Gamma-ray bursts, or GRBs, are some of the most energetic and mysterious events in the universe, and their connection to black holes is nothing short of fascinating. These intense flashes of gamma radiation can outshine entire galaxies for mere seconds or minutes, releasing more energy than the Sun will emit over its entire lifespan. Scientists have long been intrigued by what causes such astronomical fireworks, and evidence suggests that black holes play a central role. In many cases, gamma-ray bursts are linked to the catastrophic collapse of massive stars, often called hypernovae. When a star many times the mass of our Sun exhausts its nuclear fuel, its core collapses under gravity's relentless pull. If conditions are right, this collapse results in the formation of a black hole. During this process, a fiery jet of particles and radiation is launched at near-light speeds from the star's core. These jets punch through the star's outer layers and beam gamma rays across space, creating what we observe as a gamma-ray burst. Another intriguing connection involves neutron-star mergers. When two neutron stars spiral into each other, they eventually collide and can form a black hole as a result of the immense gravitational forces at play. The merger produces intense gravitational waves, and the aftermath often includes powerful gamma-ray emissions. These events give us unparalleled insights into the birth of black holes and the extreme physics governing their formation. What makes gamma-ray bursts so essential in studying black holes is their role as cosmic signposts. They help astronomers locate black holes in distant galaxies, opening a window into the universe's most violent and energetic processes. As we unravel the puzzles of gamma-ray bursts, we're not just learning about spectacular explosions, we're uncovering the very pathways through which black holes are born and grow, deepening our understanding of the universe's most enigmatic giants. Gamma-ray bursts, often abbreviated as GRBs, hold a special place in the realm of cosmic phenomena due to their staggering energy output. When these bursts occur, they unleash in a matter of seconds as much energy as the Sun will produce over its entire 10 billion-year lifetime. To put it into perspective, a single gamma-ray burst can emit as much gamma radiation as hundreds of thousands of stars shining simultaneously. It's like witnessing a flash of light so intense that it outshines entire galaxies, but only for a fleeting moment. But are they truly the most energetic events the universe has to offer? For now, they are contenders at the top of the list. These explosive events are believed to originate from catastrophic processes such as the collapse of massive stars, sometimes called hypernovae, or from the merger of neutron stars and black holes. When such an event occurs, it channels an enormous amount of energy into tightly focused jets that blast into space at nearly the speed of light, producing the intense gamma-ray emissions we detect. The energy behind gamma-ray bursts dwarfs many other cosmic events. For comparison, a supernova, the explosive death of a star, releases about 10 to the 50th power ergs of energy, while a GRB can release over 10 to the 53rd ergs in just seconds. That's a million times more concentrated energy, condensed into a brief but spectacular flash of gamma rays. Scientists continue to investigate these powerful bursts, trying to understand their origins and what they reveal about the universe. Are they the ultimate explosive phenomena? For now, they stand as some of the universe's most energetic and mysterious events, challenging our understanding of physics at its most extreme. As technology advances, perhaps one day we'll uncover even more energetic cosmic surprises lurking in the depths of space. When pondering the vast expanse of the universe, a few celestial spots stand out as the most promising candidates for harboring life. One of the most familiar is our own solar system, especially the planet Mars. Once believed to be a dry, barren wasteland, Mars has shown signs of ancient water flows and perhaps even underground reservoirs today. Scientists are eager to explore its subsurface for microbial life, as liquid water is a crucial ingredient for life as we know it. Beyond Mars, icy moons orbiting giant planets could be cosmic gold mines for extraterrestrial life. Europa, a moon of Jupiter, has a thick ice shell concealing a liquid ocean beneath. This hidden water might harbor simple life forms, utilizing chemical energy from the planet's volcanic activity and radiogenic decay. Similarly, Saturn's moon Enceladus ejects plumes of water vapor and organic molecules into space, hinting at a subsurface ocean that could, under the right conditions, nurture life. Stars and their surrounding planets in the habitable zones, the Goldilocks zones, are also prime focuses for astronomers. Here, planets are neither too hot nor too cold, allowing water to stay in liquid form, which is essential for life. Kepler and other space telescopes have identified dozens of these planets, sparking excitement about worlds that might have the perfect conditions for life. Even farther afield, the icy clouds of Titan, one of Saturn's moons, host organic molecules and lakes of liquid hydrocarbons, creating a unique environment that, while very different from Earth, still sparks curiosity about potential life forms adapted to its extreme conditions. The universe's most mysterious corners, cold, dark, and seemingly inhospitable, may yet hold secrets about life's resilience and adaptability in ways we are only beginning to imagine. The quest to detect signals from extraterrestrial civilizations has led scientists to develop and deploy some of the most sophisticated and sensitive technologies in the world. At the heart of this search are large radio telescopes, which act like cosmic earphones, tuning into the universe's faint whispers. These colossal dishes, such as the Arecibo Observatory and the Very Large Array, gather weak radio signals from distant star systems, analyzing them for patterns that could indicate intelligent origins. Their xenon-like sensitivity allows us to hear even the faintest cosmic murmurs, making them vital tools in the hunt for extraterrestrial intelligence. Complementing these are optical telescopes equipped with high-powered detectors that scan the skies for laser signals, bright, focused bursts of light that might be used by advanced civilizations for communication. Instruments like those on the Keck Observatory or the Large Synoptic Survey Telescope help sift through countless stars, hunting for transient laser flashes that could indicate artificial signals amid the cosmic noise. To enhance the search, scientists employ signal processing techniques powered by artificial intelligence and machine learning algorithms. These digital brains can sift through enormous volumes of data rapidly, recognizing subtle patterns or anomalies that human eyes might miss. They can distinguish potential extraterrestrial signals from the cosmic background and terrestrial interference, reducing false alarms and increasing our chances of success. Space-based observatories are also playing an increasing role in this cosmic telephone game. Satellites orbiting Earth can avoid the interference caused by our planet's atmosphere and human activity, offering a clearer view of the universe's faint transmissions. All these tools, massive radio arrays, precision optical instruments, advanced data analysis algorithms, and space-based observatories form a grand symphony of technology. Together, they are opening a window into the deep cosmos, striving to answer the age-old question, are we alone in the universe? Imagine the profound ripple effects that would follow if we discovered extraterrestrial life, whether it's microbial life lurking beneath the icy surfaces of moons like Europa, or more complex organisms in distant exoplanets' habitable zones. The implications stretch far beyond the academic, touching the very roots of our philosophical, religious, and scientific beliefs. It would fundamentally challenge our understanding of the universe as a place teeming with life, reshaping our place within it. On a scientific level, the discovery would ignite a new wave of exploration and inquiry. We'd need to develop advanced technologies to study these alien ecosystems, learning how they originated, evolved, and sustained themselves. The search for extraterrestrial biology could help answer one of the biggest questions: are we alone? If we find evidence of life sharing biochemistries similar to ours, it could suggest that life might emerge readily under the right conditions across the cosmos, bolstering the idea that life is a common outcome rather than a rare cosmic fluke. On the philosophical front, alien life would force us to reconsider our uniqueness and our role in the universe. Are we merely one of countless civilizations, or does our form of life have a special significance? Such discoveries could ignite new debates about consciousness, intelligence, and the potential for interstellar communication or even contact. Furthermore, discovering extraterrestrial life could propel technological and medical advances inspired by alien biology. Think of new medicines or materials derived from alien ecosystems, unlocking innovations previously thought impossible. Ultimately, finding life beyond Earth would be among the greatest scientific milestones in history, opening doors to questions and possibilities we are only beginning to imagine. It's a cosmic domino, toppling beliefs, sparking curiosity, and rewriting the story of our universe. Detecting alien life is one of the most captivating quests humanity has ever undertaken, but it's riddled with challenges that make the task daunting. First, the sheer distances involved are staggering. Even if a planet is just a few dozen light-years away, that means any signals or evidence of life could take decades or centuries to reach us, and that's assuming we're looking in the right direction at the right time. The universe is vast, with billions of potentially habitable planets, making it like searching for a needle in a cosmic haystack. Another hurdle is distinguishing genuine signs of life from false positives. Many chemical signatures we might associate with life, such as methane or oxygen, can also be produced by non-biological processes. So, scientists have to be extremely careful in analyzing data, ensuring that what they detect isn't just natural planetary chemistry. This meticulous process requires highly sophisticated instruments and careful interpretation, which are still evolving. Furthermore, life itself might not resemble anything we know. We tend to look for Earth-like life, but extraterrestrial organisms might be based on entirely different biochemistries, making them harder to identify with existing biomarkers. The potential for alien life to exist in a form that's radically different from biology on Earth complicates efforts to recognize it. There's also the challenge of confirming an absence of contamination, both terrestrial and extraterrestrial. Ensuring that signals or potential biosignatures aren't just the result of our own contamination or misinterpretation is crucial, especially before claiming a groundbreaking discovery. Lastly, the philosophical and societal implications add layers of complexity. Conforming alien life would revolutionize our understanding of the universe and our place in it. Yet, the scientific community must tread carefully, ensuring discoveries are robust and unambiguous to avoid false alarms or premature conclusions that could ripple through society and unsettle our worldview. As we peer closer into our cosmic neighborhood, the possibility of microbial life existing on planets within our solar system becomes an exciting and tantalizing question. While Earth remains the only planet known to harbor life, scientists have uncovered intriguing clues suggesting that some of our neighboring worlds might host the basic ingredients needed for life, mainly microbes capable of surviving in extreme environments. Take Mars, for example. Evidence from rovers and satellite missions indicates that the red planet once had liquid water on its surface, and underground water ice is present today. The detection of organic molecules, building blocks of life, along with ancient riverbeds and mineral deposits formed in water, fuels speculation that microbial life might have thrived in its past. Subsurface habitats, protected from radiation and harsh surface conditions, could still harbor microbial communities lurking beneath the surface. Beyond Mars, icy moons like Europa orbiting Jupiter and Enceladus circling Saturn are prime candidates in the search for extraterrestrial life. Beneath their thick ice shells lie vast oceans of liquid water, kept in a liquid state by tidal heating, gravitational flexing caused by their parent planet's gravity. These hidden seas are believed to contain the necessary chemical ingredients and energy sources to support microbial life, similar to extremophile microbes living around Earth's deep-sea hydrothermal vents. In fact, geysers erupting from Enceladus have revealed plumes rich in water, organic compounds, and other vital chemicals, sparking hopes that life could be thriving in those alien waters. While no definitive proof of extraterrestrial microbes has been found yet, these environments remain the best candidates for hosting life, worlds where the conditions, though extreme, may still be hospitable to tiny, resilient organisms. The quest continues, bringing us closer to answering one of humanity's most profound questions: are we alone? Detecting planets that orbit stars beyond our solar system, known as exoplanets, is a task that pushes the boundaries of modern astronomy. Since these worlds are incredibly dim and distant, they are usually drowned out by the unbearable brightness of their parent stars, making direct imaging a challenging feat. Instead, astronomers rely on clever indirect methods to unveil their existence. One of the most prolific techniques is the transit method. Imagine a planet crossing in front of its star from our vantage point, causing a tiny periodic dimming of the star's light. By carefully monitoring the brightness of stars over time, telescopes like Kepler have identified countless exoplanets through this telltale dip in light. These transits not only confirm a planet's presence, but also reveal insights into its size and orbit. Another powerful approach is the radial velocity method, sometimes called the Doppler method. When a planet orbits a star, its gravitational pull causes the star to wobble slightly, moving toward and away from us in a tiny dance. This motion shifts the star's spectral lines due to the Doppler effect. By measuring these subtle shifts over time, scientists can infer the presence of an orbiting planet and estimate its mass. There are also other, more specialized techniques like direct imaging, where astronomers use advanced telescopes and coronagraphs to block out starlight and possibly spot the planet directly, especially for planets far from their stars. Gravitational microlensing takes advantage of the bending of light caused by a massive object, which can reveal planets even in distant parts of our galaxy. Together, these methods form a triumvirate of discovery, allowing us to find, study, and understand worlds far beyond our solar system, each one a tantalizing hint that our universe is filled with countless planets wandering through the cosmic sea. Discovering potentially habitable exoplanets opens a window to questions that have fascinated humanity for centuries. Are we alone in the universe? Finding planets that could support life pushes the boundaries of our understanding of where life can exist and what conditions are necessary for it to thrive. It's like unlocking a cosmic puzzle piece. Each discovery brings us closer to knowing whether life beyond Earth might be more common than we ever imagined. These planets orbiting stars in the so-called habitable zone, where temperatures could allow liquid water to exist, are prime candidates for future exploration. The significance goes beyond simply seeking life. It challenges our understanding of biology, chemistry, and planetary science. If we find life on another planet, even in primitive forms, it would confirm that life is not a rare cosmic accident. Instead, it could be a natural outcome of the universe's chemistry and physics, making the universe seem a lot more life-friendly than previously thought. Moreover, studying these worlds helps us understand planetary processes, climate dynamics, and atmospheric compositions, offering clues about Earth's own history and future. Potentially habitable exoplanets also inspire the development of new technologies and scientific approaches. Missions designed to analyze their atmospheres for biosignatures, indicators of life, drive innovation and international collaboration. The quest fuels our curiosity and our desire to explore, ultimately reshaping our perspective on humanity's place in the cosmos. Each discovery expands the horizon of what is possible, transforming the universe from an unknowable expanse into a landscape filled with countless worlds, some perhaps teeming with life, just waiting to be explored. When it comes to exoplanets, those incredible worlds orbiting stars beyond our solar system, scientists are just scratching the surface of understanding their atmospheres and compositions. Thanks to advanced telescopes like the Hubble Space Telescope and the more recent James Webb Space Telescope, we can now analyze the light that filters through or reflects off these distant planets, revealing tantalizing clues about what they're made of. One of the key techniques is transmission spectroscopy. When an exoplanet passes in front of its host star, some of the star's light filters through the planet's atmosphere. By studying the resulting spectrum, scientists can identify signatures of gases like hydrogen, helium, water vapor, carbon dioxide, methane, and even more complex molecules. These fingerprints tell us not only what an exoplanet's atmosphere is composed of, but also give hints about its climate, weather patterns, and potential habitability. Beyond atmospheric composition, researchers also delve into the planet's overall makeup, whether it's rocky like Earth, gaseous like Jupiter, or a mix of both. Interestingly, some exoplanets show signs of thick, hazy atmospheres or even clouds, which can complicate the analysis but also point to dynamic weather systems. Surprisingly, a few planets seem to harbor water vapor without necessarily having oceans, raising questions about their potential to support life. Studies have also uncovered atmospheric escape, where lighter gases drift away into space, especially on planets close to their stars, experiencing extreme heat and stellar winds. Such findings help us understand not just what these planets are today, but how they might have evolved over hundreds of millions or billions of years. Every discovery adds a new piece to the cosmic puzzle of what makes planets habitable or not in our vast universe. Exoplanets truly push the boundaries of what we think is possible in planetary formation. Imagine discovering a planet orbiting a star so different from our Sun, like a giant gas planet blazing so close to its star that it orbits in less than a day, or a rocky world located in a star system that's billions of years older or younger than our own. These findings throw a wrench into the neat models we've developed based on our solar system. Traditional theories suggest planets form within protoplanetary disks, swirling clouds of gas and dust around young stars, gradually building up from tiny particles to massive bodies. But some exoplanets defy these expectations. Hot Jupiters, for example, are massive gas giants residing perilously close to their parent stars, where conditions should be too harsh for their formation. Instead, scientists think these giants may have formed farther out and then migrated inward, raising questions about how exactly planetary migration works and how common such processes are. Then there are planets orbiting stars in environments previously deemed hostile or unlikely, for instance, around pulsars or in binary star systems with extreme gravitational interactions. How do planets manage to form and survive in these turbulent neighborhoods? Such discoveries imply that planet formation might be more adaptable and resilient than we once believed, capable of occurring in a myriad of cosmic circumstances. Furthermore, the sheer diversity of these worlds hints at alternative formation pathways that don't quite fit the canonical model. Do some planets form from gravitational instabilities within the protoplanetary disk rather than accretion? Are some planets captured wandering through space, snuggling into new orbits around stars? Each new exoplanet discovery compels scientists to reconsider and refine their theories, opening up a universe of questions about how planetary systems come into being and whether Earth is truly the rule or just a fascinating exception. Exciting new missions are on the horizon, designed to unlock the secrets of distant worlds and deepen our understanding of exoplanets. One such mission is the James Webb Space Telescope, often called the successor to the Hubble, but with a far more powerful infrared eye. Launched in late 2020, it is equipped to analyze the atmospheres of exoplanets in unprecedented detail. Webb's ability to detect specific molecules like water vapor, methane, and carbon dioxide could reveal not just the composition, but also the potential habitability of these alien worlds. With its high sensitivity, it can even peer through clouds and atmospheric hazes that often obscure observations, giving us a clearer picture of the planet's true natures. Meanwhile, the European Space Agency is preparing the Ariel mission, set to launch within the next few years. Designed explicitly to study the atmospheres of hundreds of exoplanets, Ariel will survey their chemical compositions and how atmospheric properties change with different planetary characteristics. This large-scale survey aims to uncover patterns that could point to planets with conditions suitable for life, or even signs of biological activity. NASA's upcoming mission, the Nancy Grace Roman Space Telescope, will also play a vital role. While primarily focused on understanding dark energy and cosmic structure, it will have a significant capability for detecting exoplanets through gravitational microlensing, revealing planets that are far from their stars or even free-floating in space. These missions, along with future advancements in ground-based observatories like the Extremely Large Telescope, promise to transform our view of distant worlds. They're not just seeking new planets, they're searching for that one telltale sign that life could exist somewhere beyond the stars.